Okay, we're now on the front lights.
You got it?
I'm on there.
Okay, great.
Which button do we poke, Dave? The 4 on the left on that
Let's see. Oh, I'm not. All right. Um, let's see. Okay. I think I'm plugged in, but why don't I have it on the screen? Okay, let me see. Um, let's see. Anybody can help? Need to turn this guy on. This is not the
F4, I think.
F4. F4.
There. You had it. You had the menu screen up. Hit it again.
The menu screen. Okay.
You want duplicate.
Okay. Let's wait a minute. What? Projector only?
No.
Okay. Duplicate.
Duplicate.
All right. Thank you.
It'll take a second to figure it out.
Let's see. Disconnect. Let's see. Project only. Still don't have it.
EVI.
Unable to connect to projector.
Yeah.
Okay, let's see. If we
Spigot down here.
it looks like it's plugged in. Yes, it used to work. Let's see. Does it have anything? Video laptop. Okay, let me see.
Just to see which button is the right button.
That's a good idea.
Because we're debugging 3 things at once. Let's make it 2.
Okay, laptop, video.
Leave off of it for a second. Just see which spigot is the right spigot. Which button is the right button. Plug into yours and hit your F4 again.
Okay, that looks like it's connecting.
It'll take a sec to
Will it do it from the locker?
yeah. Just takes a minute to sort it out.
Okay,
All right.
there you are.
So that's the one. So let's take this and plug it in and hit
Yeah.
F4 again. And select both rather than a duplicate rather than.
Okay. Duplicate. Okay, yeah, we are. Okay, that's good. Okay. Phew. Let's turn this guy off. And okay, let's talk. Slideshow from the beginning. Okay. Thank you, Kevin. All right. This is a Silicon Valley Fourth Interest Group, and I'm CH King. And this morning, I think the title was wrong. It's the Beetle robot. Okay. Now, let me see. I just forgot to change the the title slide. So the summary, I will talk a little bit about this Beetle bot. That's my robot. And I'll just talk about the motor drives, ADC sensors, and one of the more interesting thing is the IR remote sensor speakers, and do some demo. I had this in running on the battery, but apparently the battery was drained dead, so I can't let it run free. But when I connect it to the computer, I hope it will run, at least turn the wheels a little bit. Okay, this is BeetleBot, and I got it on Amazon for $59. So it's a fairly decent robot. Got all the things you need to get it to run. Okay. Don will build his L robot, but he's busy. I don't know whether he'll be able to do it. So this is actually the plan B. If Don didn't get his robot built, we will have some robot. And if we are going to get a booth at Maker Fair, at least we'll have something to do. And I was looking at the Amazon a couple of days ago and found there are more robots at the same price range. And I think there is a much better one than this one. But I think they are all coming from China. and they probably share all the components and all the designs. But one of them looks much better than this one, because this one lots of wires, and it doesn't look like a robot. The the other one got that everything cleaned up a bit, so it looks much better. So here, the two wheels, and the they use actually 4 control signals to drive the robot, and the controller is underneath here. So it has four input, and according to the documentation, you need to drive it with pulse width modulation, and so I tested that a little bit. It really doesn't use the pulse width modulation. It does not use the pulse width modulation. What it does is just use an average. So if you reduce the pulse width modulation duty cycle, the motor will run slower. Okay, so it's just a digital control. I mean, kind of analog control, but it's used pulse width modulation. If the duty cycle, you reduce the duty cycle, the motor turns slower. And so this is the pulse width modulation. I use it uses 4 output to drive it. So here I used to let me see. Yeah, remember I had an experiment with the digital clock. I remember I got the 6 servo to turn 6 needles, and the needle indicate 0 to 9 and 0 to 5, and this way it you can read it using basically 8 meters. So I just use that the code, and since I only need 4 signals, and the way the motor controller works is it accepts the 4 inputs, but 2 of the inputs, if you one of the input you send that pulse width modulation, it will drive the one wheel forward, and another, if you turn the pulse width modulation, it will drive the motor backward. So you have 4 lines, and then you can turn the 2 wheels either forward or backward, or any combination of. So this is the code. S1 drive, say, the right wheel forward. S2 drives the right wheel back. And then S5 drives the left wheel forward, and S6 drives the left wheel backwards. So this is how it controls. And now, if I for a motor robot, for 2-wheel motor, what you need is go to drive forward, back to drive it backwards, and left turns on only the right wheel, and the right turns on only the left wheel forward. Okay, you can have many other combinations, but basically this is how you would drive them. And then this signal turns the pulse width modulation fully on, and 0 reduce the duty cycle to 0. FF increase the duty cycle to 100%, And then according to this to the demos there, C0, if you just turn the left, make a right turn, you don't turn the left wheel fully on. You turn it about 2/3 or three-quarter. Give it 3/4 of the power. So this is how the demonstration program indicates. So, but I quickly found that the pulse width modulation is not. It does not use the periods or the duty cycles to control. It's actually send out the signal, and it uses the average power. So, you know, if I don't mind use the full power to drive it forward and backward, you just turn these 4 signals fully on or fully off, and that would drive it at full speed. So here, if you don't use the power, the pulse width modulation, things are much simpler. You just turn the 4 bits, turn one of the bits on or off, and you achieve the same, basically the same effect. The wheels just turning fully on or fully off, fully forward or backward. But I think it is okay for this robot. It really does not need that type of fine control. So just do the digital control is okay. And then there are lots of sensors. So here, if you see, these are IR sensors. So one IR LED emits and the receiver receives. So this one, you can see an indication. But this one doesn't have indication. The indication was broken, but it worked. So if you have some obstacle in front of it, the line will turn on or off. So the demonstration program uses ADC. The Arduino has 6 ADC lines, analog input. So you can read the voltages on these 6 input lines. And this is the code to read the ADC. You just write a control signal into a particular port, and it would and when you read it back, I'm sorry. Yeah, you write a control signal to turn on a particular A analog channel, and actually it has only one A to D converter, but it accepts up to 16 different inputs. So you just switch the multiplexer, and then you can read any one of the 6 analog lines. Only 6 lines are brought up to the edge of the chip and brought to the robot controller. So basically, you just say turn one multiplexer, and then read the output. But one thing we have to be careful was that once you set up the start conversion, you have to give it a short delay so that the conversion can complete and the data will be available. So this is why there's a 1 millisecond inserting it. And then you can basically, once you can drive the motor for wheels forward, backward, left, right, and then you can use the 2 sensors here to decide which way you want to turn. So this is the very simple program to do that. However, the sensors, the analog input accepts the data, accept the analog voltage from 0 to 5 volts, and it does conversion. But when I did the conversion, it always turned to be 0 or FF. That's because this this sensor, the sensor has already lots of electronics in it, and it also has a pot to set the trigger level. So the sensor actually does all the conversions and all the right logic. So you really here you really cannot read the voltage on the analog input. You are actually reading what was processed by the ADC converter. So you only get the 0 and 1. And the ones you can only read 0 and 1, well, you don't really need the A to D conversion, right? So here it is the so that's the you use the ADC to do the A to D conversion, because the ADC only reads 0 or FF, and there's no reason to use the ADC. And you just read the digital signal directly, okay? And you got the 0 and 1, and that one you can use that read all the sensors and pick whatever the bit you want to see, and then you can decide whether to drive it forward, drive the backward, drive to the right or left. So this is much simpler. Okay, now it is controlled by this. You can control it remotely with this remote controller, and it was very interesting. So I spent lots of time try to read the remote. You know, the Arduino, it has a fairly extensive library to do all these things. So it doesn't it has for example the motor drive. You can, in the Arduino program, it assumes you are outputting a power pulse width modulation wave, and you can actually specify the duty cycle of that wave in the digital output, or they call it analog output. So it is the analog output in Arduino. You just specify the duty cycle, and it would automatically put out the pulse width modulation wave. And likewise, there is the a library routine which will read the remote control. But since I'm running everything on the E4, I don't have that library. So I just try to see what was the signal and try to decode it myself. So here is the typical waveform that's sent out by one of these remote controllers. Okay, so this way the IR signal are modulated at 38 kilohertz. So it is sending out pulses at 38 kilohertz, and the pulses are grouped in groups, and then the actually this receiver, this IR receiver actually does all the demodulation and decoding. So when you read the signal from the IR receiver, you are seeing, for example, here you are seeing a low. Let me see. high, and the signal is high and low for this amount, and then high and low, and so it demodulates and output the appropriate high and low signals. And high and low signals are in such a way that first it pulls down the line. Normally, when there's no signal, the line is kept high. And when it sees this one, it pulls down low and give a high and pull down low and give a high and low. So you got a high and low signals, high and low signals. But the width of this on signal varied. Okay. So you first have a big signal, and then you have so the signal is this is a short one, a medium one, and a long one. Okay, and the long one is the stop bit, and then each bit this wider, the medium one is a logic 1, and the short one is logic 0. So this way, you first got the stop it, and then you get 1 and 0, 1 and 0, and then at the end there's some stop bits. So looking at the modulation is 38 kilohertz. So these pulses are only about 30 microseconds. And then there are many of them. And so this is about the widest pulse is about 2.4 milliseconds. Okay, actually 2.5 milliseconds. 2.5 milliseconds, you have 10 of them. Well, that's 20 milliseconds. And generally, from this particular, all the different remote control output different formats of signals. So this one is the simplest. So it outputs a 32-bit number. For each pulse, it outputs a 32-bit number. And so after I got this thing going, I got all the TV controllers in my house, and just click them and to see what kind of form, what kind of waveform they produce. And most of the TV controllers output much more complicated signals. I think probably 60 bits or 64 bits of information. And so this one is the simplest. It only put out the 32-bit. Okay, once I have once I was able to read these pulses, I just assemble these pulses as fast as I can, and I was able to see what the output are, what the output pulses are, and then in software I can decode this thing. So you see here the pulse width modulation on and off. So all the off signals are 0.6 millisecond. And the on signal, the stop bit is at 2.4 millisecond. And then the bit 1 is 1.2 millisecond, and bit 0 is 0.6 millisecond. So this way, if you can sample these signals fast enough, you can decode the pulses from the remote control. Okay, so this is the code to decode this remote signal. So normally idle, when the signal is idle, when there's no signal, the level is high. So you wait for low, And when the signal is low and you want to detect the up the up edge and the high, just wait until the level goes high.
Wait for low.
Yeah, this low and high, just wait for the low signal or wait for a high signal. And the bit width is that when you turn, when the bit is on, you want to count how many cycles you want to determine the width of it. So you wait until it's high and begin counting. And after that, you get that number which shows you how many cycles this high level lasts. And so the stop it to determine that it is a stop it. So the stop it in this system, I determined that the big high signal, the stop it, is between 180 cycle and 280 cycle. It's generally 200 cycle, 200 hex cycles, so 512 cycles. So I'm waiting for this stop it. And once I get the stop it, then I'm going to read 32 bits of the subsequent pulses. So this way I can get one 16-bit word out of the read 16 pulses and determine the bit 1 and 0. And then get code, you wait for the stop bit and get the 16-bit word and get another 16-bit word and wait for 100 milliseconds so that all the stop bits passes by. So with that, I'm only using these 4 bits. These 4 up and down, left and right, and the center. I'm reading only these 5 buttons. And I don't know what these buttons are, and I just read these 5 buttons and found out that the signals are for the right arrow it's 5AA5 and FF. Okay, but only all the buttons generate high. Generally first word is 00FF. So I skip that one and read the next one, and the next one seems to have significantly different bit patterns. So I was able to decode this and then putting here in a loop that if I read this button, I'll drive it right. If I read this button, I drive it left, and drop it go, drive it forward, V, drive it backward. And if I have the center button, it will stop. Now this is the very simple. Once you can read the IR remote, then you can use it to control the robot. And in Don's robot, his robot kind of making lots of noise, and it's very interesting in that there's when it's distressed, when it goes forward, it makes one sound. When it drives backward, when it does different things, it would generate different noises. And that was interesting, and I tried to emulate that. So here, this is the code. Remember, I have used the Arduino to play a three-part fugue of Bach. So this is the code from the 3-part fugue. So I can control three different speakers, and make them generate different different square waves. So here I just use because these two channels are used by the motor controller, and I have this channel left, so I can use this channel to generate some voice. But I haven't incorporated everything into the program yet. Okay, the hard part of doing a robot is actually the interrupt control to how to do the interrupt. And I talked about this interrupt a number of years ago. And so I actually did all the interrupt control code I have a Arduino, which is actually fourth is interrupt driven. Okay, so the fourth is running in background, and when you hit a key, that key would interrupt the system, and that key gets processed. So it's and so in foreground you can do any kind of things, but the fourth is running in the background, activated on by keystroke. So that one worked pretty well at the time, but when I tried to reactivate it, nothing worked. But I have all the code that I developed to control the interrupts. So here in the Arduino, it has I forgot about the 20 to 30. I think it can have up to 30 interrupt vectors. So here you can initialize all the interrupt vectors. Try to avoid the reset vector, okay? Because in my for system, the reset vector is always calling the code star, okay? So avoid that one, and then the next quite a few numbers in interrupt can be used. So you first initialize all these interrupts by putting out a jump to return instruction. Okay, so once you got this, this is I return 9518 is the return from interrupt. So all the interrupt vector just jump to that return from interrupt instruction, and this make them all no ops. So if you want to do anything with any of the interrupts, what you do is you give it an address. This is the interrupt processing routine, and you specify the vector. The vector is from 1 to maybe, I think 1 to 20 or something. And then it will jump to this address if this interrupt is activated. So this way, I can rewrite the interrupt vector table to handle as many interrupts as you want to have your system. And another thing is that I don't have an assembler for the Arduino. So here is the assembler. Okay, so I need several instructions: return from interrupt, and I need SEI, so enable global interrupt, and CLI, that's the clear global interrupt. Of course, no op, and SBI flips 1 bit, and that bit controls the default LED on the board. So this one is a nice nice thing to test. So you need to when interrupt hit, in fourth, everything's on the return stack and the data stack. So you really don't have to save much, but except the S register, the state register. So what you want to do when the interrupt hit is to save the S register, and before you return from the interrupt, you pop the S register back. And I think that's all you need to do to handle an interrupt on the system level. So all these things are defined as instruction comma, and it just writes a particular instruction into the dictionary. And so that's all you have to do with the assembler. And of course, I don't need a full set of instruction, but I can actually implement all the instructions, extended this assembler fully. But no, I only have to use it for interrupts. So these are the instructions I need to service some simple interrupts. So one very interesting interrupt is the watchdog timer, and for most of the microcontrollers, this watchdog timer is a default. It's always there. And so in the Arduino chip, it has the watchdog timer. And I thought, well, I'm not using it for watchdog timer. I'm just using it as a periodic interrupt to service the input and output functions for the robot. So basically, I just need an interrupt at the 0.1 second level. So this is the how you do the watchdog timer. So here you can enable the watchdog timer, and this I really cannot do it in high level. I cannot do it in fourth, because when you enable the watchdog timer, basically you set up the period of watchdog timer, and this period, this interrupt control register has to be written. These two instructions, the second instruction has to be written within 4 cycles. Okay, so so I really cannot do it in fourth, and this has to be done in assembly. You first clear the global interrupt, and this WDR instruction reactivates the watchout timer, and then you set up the one control, set up the control register, and then you set up the delay. Okay, so it has the watchdog timer has many. It's the down counter. Okay, it's interrupted from 32 kilohertz. I think 32 kilohertz crystal, and it just has a prescaler. And then the second instruction set up the prescaler so that you can set up the period that the watchout timer activates. So these two instructions has to be executed within 4 cycles, and that's the most critical one. And that re-enables the global interrupt, and this way you set up the WTD, and the WTD, the interrupt, when it hits, it has to push the S register, save the S register, and just flip a bit to turn the LED on or off, and then restore the status register. So here, this is the Beetle bot robot, and at this moment, I can control everything in the foreground. I haven't done anything in the background, and the interrupt is that if you set things up and turn on the interrupt, the system just dies. Okay, that's normally what happened. And so I still haven't figured out what's the problem. So I only have this in running, and everything has to be run in the foreground. But later on, I think I can get the force to run in the background as a background task by vector the key to vector the key function to the receiver line. Okay, and then I can also vector the IR receiver. So only when the IR receiver sending is activated, I have a service routine, interrupt service routine to receive the code. And then in the foreground, what like Don says, is the I have instinct level, and that's the interrupt and the reading all the input and deciding what the output has to be, and the instinct level and behavior level, and then the goal level, right? So the goal level will behavior level could I think I'm not clear at how would I do it. I think this thing is simple enough so that one level of control will be one foreground task will be sufficient. Okay, so the behavior and the goal level could be the same, but I don't know. I just want to get the basic function to work, and I want to have the interrupt to work reliably, which it does not, and then build everything from there. So this robot is quite interesting in that it has most of the functions, and I think it's easy enough for me to get through it through a serial cable. And when I think in here, the force system, the E-force system is set up so that after the whole thing is working, you can revector the kick boot. So the boot function can be revectored to any application, and everything gets saved into the flash memory, so that next time when you turn it on, it will run that boot function. And let me see. I think let me just do some demo, if I may. Okay, so here, so the fourth is running. Actually, it's running the robot code, and when you hit the return key, and then send a remote signal, it will break out. But if I say code, it re-enter that routine, and I hope that this guy is going to respond. Yeah, if you can see the wheel is turning. If both wheels are turning, and then back, they're turning backwards, and this one to the left. Yeah, this one is turning. And turn this thing off, and that's all. So that's, and here it is showing the key. It just read, okay. So you can see it's responding to the okay. Yeah, you know, I think it unfortunately. Okay, hey, stop. So if you yeah, you want, you can come and push the buttons and see how it works. Okay. Yes.
You considered getting an IR sender for your laptop and talking to it that way?
Oh.
That's a lot.
No. I think this this remote control is very nice. Yeah, because you really the purpose of it is that you don't connect it to a computer, and it will run free. Okay.
So that doesn't go to the Arduino, it goes straight to the motor.
No. It goes to the, you see the receiver. Receiver is here. If you can see the receiver will flip. Well, you see. Yeah. Okay. So it's receiving. So this is very nice. This controller, it actually the visual response that you can observe from all these components.
So the processor is a regular Arduino?
Yeah, it's a regular 328P. Okay.
So if you want, you can stack like shield boards and stuff on top. Like if you want to talk to your robot. Bluetooth.
Yeah. So this actually this robot is very. I think this is very interesting in that. You know, I worked with Arduino for a long time, but every time I have to use the wire to stick it and connect it, it's kind of awkward. This was one of the thing we did the challenge. Yeah. This is, I think 4 or 5 years ago, we have a 4th-day challenge, and people were able to lead the LED panel for some interesting things.
Yeah, once in a while I see a clock with LED line.
Yeah. So this is my development system, okay? And you have Arduino there. You have to have wires sticking out to some experiments. And this one is the programmer. Yeah, and you can reflash the entire chip for I just clean up everything and put my 4th in, and this is how everything worked. I think the shield they installed on top of the Arduino is very interesting in that you know these input and this is these are the 6 input analog input, and there are 12 digital input and output. So this it has all the signals, but it's very difficult to wire. And generally, finally here, I found that all these different sensors and motor drives are using these 3-wire plugs.
DF Robot. DF Robot. It's the company that I found that has that same type of thing.
Well, there are many, right. Yeah.
That
all the
one
all the sensors and the server, and the sensors and drivers and everything. They kind of adopted this 3-wire, and then the shield actually has the signal there, and then the power and the ground, so you can plug this in directly.
Right.
And I think that's a very, it pretty much becomes standard now. Okay. So
And
you
I think DF Robot is using it too, and they've got a whole bunch of different boards too.
Right. You don't need you just need one board which has the which turns every of these signal pin into three pin acceptor. Yeah.
Or trial.
Yeah, and you can just plug this in a row.
Yeah.
Yeah.
It's wonderful.
Yeah.
They're running SPI on that interface or?
No, they just bring out the pins so that every digital and analog pin has a mating ground and power.
Yeah.
So you just have this trio on every pin. Okay. So it's just combining that onto a
So you have multiple connections.
Yeah.
That are all these.
Yeah. And you
everything is going to one power connector.
yeah, and if you yeah. If you want to take a look at this this robot, and you can see the rows of pins that you can plug in very conveniently.
Love it.
Yeah. So I think unless you design your own robot and you have all the all the sensors, you have all the sensors installed on the same board, you don't need that. But if you want to build a general purpose kind of experiment, and this is just a perfect.
Proof of concept.
Yeah. Right. So I think this would do lots of. So if I have known this, lots of things I have done different. I would do differently.
Within the last year that I've been finding this.
Yeah.
Very recent that they've been doing this.
Well, I think it's just that these several Chinese companies are making these robot kits, and they all use probably the same sensors and the drivers. And
the reason I found DF Robot was because of the sensors. Now they also have little small boards for each sensor. Every sensor has its own board.
Right. Yeah, take a look here. This IR sensor, they just have a ton of this thing. But I still haven't. I found a company which is making 40 of these modules.
Yes.
But I only want these 3.
I bought a kit with like 27.
Yeah, right.
I used maybe a dozen at this point.
Okay, that's all I have.
That's all?
Yeah, that's all. Okay, thank you. Yes, I ordered 2.
Yeah, much more powerful. And low power. I can get it supposedly down to 50 microamps.
Yes.
But I don't.